We've been looking at scalar products, how we calculate them, and the kind of things that we can use these to calculate. One thing we're going to look at in this video is there's a few key properties associated with scalar products that you have to be able to do. Now, remember what we've done so far is we've looked at what two different forms scalar products take. So the A dot B equals A1, B1, A2, B2, A3, B3 form. And then the other form, which is A dot B equals a magnitude of A, magnitude of B, cos theta, where theta is the angle between the two vectors. So we've looked at how we can use these. There are a few other things that need to be built in and understood that we can then bring in and apply when we're doing calculations with them that might make our life a lot easier. Three key ones, and we're going to look at all three here. I'm going to show you what they are, prove to you that they work, and then give you a couple of examples. Now, the first of these three is the property of it being commutative. What that means is if I've got two vectors, A and B, and I do A dot B, that is the equivalent of doing B dot A. So I can use this sometimes in order to be able to make my calculation a little bit easier and also be able to use and manipulate vectors a little bit better. Now, it's a fairly straightforward one to prove. Imagine I've got two vectors. My vector A, which is A1, A2 and A3, and my vector B, which is going to be given by B1, B2 and B3. Now let's take A dot B. So let's do the scalar product of both vectors. So A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. Now each of these is a product, i.e. a multiplication calculation. So what I'm able to do is switch them round. Remember, 2 times 3 is the same as 3 times 2, so A1 times B1 is the same as B1 times A1. So that's the equivalent of B1 A1 plus B2 A2 plus B3 A3. Now this here is the equivalent of taking B dot A. It's the equivalent format of doing that. So what I've done here is I've proven that therefore A dot B equals B dot A. It's a fairly straightforward one to prove. The second property that we want to work with and that's associated with vectors that we need to remember is that they are associative. So what I can do in order to think about that is imagine I've got A dot B plus C in a bracket. So I want to add these two vectors and then take the dot product. Now that's the equivalent of essentially multiplying out the brackets with a scalar product and putting it in this form here. A dot B plus A dot C. So I can take the scalar product of the thing outside the bracket with each element in the bracket and then add the answers to these. And again, it's a fairly straightforward one to prove. Imagine I've got my three vectors, so A I'm going to take as A1, A2 and A3. The vector B I'm going to take as B1, B2 and B3. And the vector C I'm going to take as C1, C2 and C3. So I've got three generic vectors there. So in order to prove this, I'm going to start with what's in the bracket. Think of BODMAS, you start with what's in the bracket. So if I take B plus C, what I then get is adding the two vectors, I get B1 plus C1, B2 plus C2, and B3 plus C3. Now, what I'm able to do at this point is then take my dot product of that. So I can now do A dot the B plus C. And all I would do is take the scalar product of A with this vector here. So I then get A1 times the first term, which is B1 plus C1, plus A2 times the second term, which is B2 plus C2, plus A3 times the third term, which is B3 plus C3. Now, what I'm going to do is I'm going to multiply out all of these brackets. So I get A1 B1 plus A1 C1 plus A2 B2 plus A2 C2 plus A3 B3 plus A3 C3. What I can now do is if I group the vector parts together with their associated parts, I can see what I get. So I'm going to group all the B's together and all the C's together with their A coefficients. So that's the same as A1 B1 plus A2 B2 plus A3 B3 plus the C parts all together, which is A1C1 plus A2C2 plus A3C3. Now if you look, this here is the format of A dot B. And this here is the format of if we took A dot C. And we're adding them together, so that's what it equals. So at this point I could say fine, so I've just shown that A dot bracket B plus C is the equivalent of A dot B plus A dot C. So I've just proven that second property. So that's our second property when vectors are associative with each other. The third property we want to work with is perpendicular vectors. Now if we take the scalar product of two vectors, A dot B, and we get 0, then A and B are perpendicular. This one again is fairly straightforward to prove. Remember our form for the scalar product, A dot B equals the magnitude of A, magnitude of B, cos theta. Now if A dot B equals 0, what I can say is that the magnitude of A times the magnitude of B cos theta equals 0. Now this occurs in one of three ways. If magnitude of A is 0, the magnitude of B is 0, or cos theta is 0. But A and B are vectors, they will have some form of a size, even if that size is 1 or a fraction smaller than 1. So neither of these two can equal 0, so it has to come from the cos theta part. So from that I could say fine, so cos theta equals 0. I know then that theta is equal to cos minus 1 of 0, which we know is 90 degrees. So the angle between the two vectors is 90 degrees. So I'd have my two vectors, my vector A and my vector B, and they're perpendicular, i.e. there's a 90 degree angle between them. These three properties of vectors are three things we need to know, remember, and work with. Now I'm going to show you a couple of examples of working with these. Imagine I've got three vectors here, A, B and C, and I want to find A dot B plus C. Well, this is where my associative property comes into play. I can remember A dot B plus C, with it in the brackets, is the equivalent of A dot B plus A dot C. So what I can do is find the scalar product of these two parts here and then simply add my answer together. So if I've got A dot B, do the scalar product with that, that is 2 times 0 plus 1 times 2 plus negative 1 times 3. 2 zeros are 0, so then plus 2, take away 3, that's equal to negative 1. Scalar product of the A dot C elements, again this one and this one, I get 2 times the negative 6 plus 1 times 8 plus negative 1 times 1. 2 negative 6's, that's negative 12, 8 ones are 8, negative 1 times 1 is minus 1. Negative 12 plus 8 minus 1 gives you negative 5. So A dot B plus A dot C in this case would then become negative 1 plus the negative 5, negative 1 plus negative 5, negative 1 minus 5 gives me negative 6. Nice, quick, easy way to do it using the associative property we have. We could do it the other way if we wanted and have A dot bracket B plus C and calculate it that way. So if we were to do the B plus C, adding these two vectors together, we'd get negative 6, we'd then have 2 plus 8, which is 10, we'd then have 3 plus 1, which is 4. We'd then take the scalar product of A with this. So what we'd then do is take the scalar product of 2, 1, negative 1 with this vector here, negative 6, 10, and 4. So that then becomes 2 times the negative 6 plus 1 times 10 plus negative 1 times 4. 2 negative 6's is negative 12, 1 10, that's 10, then take away 4. Negative 12 plus 10 is negative 2, take away 4 is negative 6. Look at that, the associative property holds. So it holds for any three vectors we've got. Could even extend it further and have three vectors in the bracket and make it an associative property of 4. So we could have A dot B plus C plus D. It works for any number of vectors within a bracket with a scalar product outside of it. Bear that in mind when you're working with it. These things can help us and make our lives a lot easier when we are working with vectors. It cuts down the calculation time and the things that we need to be doing in a calculation with them. Another example for you, if I give you this information here, so I'm going to tell you the magnitude of A is 8, the magnitude of B is 10, the magnitude of C is 4 root 3, and I want to find A dot bracket B plus C, and they're set up in this scenario here. Well, this is where it really comes into play. Now, if we had the vectors A, B, and C, we could just do this if we wanted to, but we don't. So we have to use the associative property and say, fine, I want to do A dot B plus A dot C. Now, this is when the second version of our scalar product comes into play. Our scalar product for A dot B is the equivalent of magnitude of A, magnitude of B, cos theta, where theta is the angle between them. And it's the same for the A dot C, except it's magnitude of A, magnitude of C, cos theta. And for this one, the theta is the angle between those. So we can substitute in the values and the information given and get both of these and then add them up. So for A dot B, we want the magnitude of A, which is 8, times the magnitude of B, which is 10, times cos 60. 60 degrees is the angle between them, that's the one we want to use. Now again, we know the exact value triangle for this one. Got our exact value there, there's 30, there's 60, our root 3, our 1, and our 2. Cos 60, adjacent over hypotenuse, is a half. So that's 8 times 10, which is 80, times a half, that gives me 40. Same for the A dot C. So I've got magnitude of A times the magnitude of C. So magnitude of A is 8, then times the magnitude of C, which is times 4 root 3, and it's then times cos theta. In this case, theta is 30. Cos of 30 gives you root 3 over 2. So it's then times root 3 over 2. So that then gives you 8 times 4. Now the root 3 times the root 3 cancels the roots, and that gives you a times 3. It's then divided by 2. So taking all this, I get 4 4s because I'm going to half the 8 here. 4 4s are 16. 3 16s are 48. What I can then do is add them together just as I would. So I've then got 40 plus 48. That gives me 88. So I know then that A dot B plus C is given by the 88. We can use any version of the dot product we want as long as we have the relevant information and we remember this associative property. It can help us with all these calculations. We wouldn't be able to do this one if the vectors were not associative with each other, i.e. if that didn't hold.